Hello, class. We are going to do a quick review of last week's work and then move to further work on the parametric component design. But I want to be sure that we can see everything in context. Therefore, the kind of things we're going to do today are, we will just do a normal GUI design of a connecting rod. Then we design that connecting rod parametrically using the GUI. Then we will now do a parametric component design using the API so that you can see what it means to design using the GUI, what it means to bring parameters in still using the GUI, and how to really go the whole hog and do a programmatical parameterization using Python. By the way, Python has become the largest programming language on earth. And that means that Python is now bigger than C, C++, C#, Java, and the other things that they are using. And it continues to be powerful and the way to program. So we're going to stick, means that our decision to start with Python, when I taught you to program last term, seems to be the correct way to go. And even though Fusion 360 allows you to program in Python and C++, we choose to stay with Python. So let me start my slideshow. And again, these slides are what you are familiar with. Last week, we started with parametric design. So we looked at, I told you that you have the IC engine, the Conrod video, the parametric video, and the V8 engine video. Today, we're adding some GIFs. I'm looking for ways of bringing down the sizes of files that I use to move things around. And I'm still looking for the best way so that the files I give you will not be too large. So, like I said before, you can navigate the S2P Africa webpage. And there are so many things that you can learn there. I hope you are doing that. And then there is still the Fusion web page. Like I told you, what I teach you in class is I'm not trying to compete with Autodesk and Fusion 360. They have their own rules, and what they do best. I don't know any group of people that can do those things better than they can. But what we are doing is to build on that and give you a university education that benefits from the valuable skills that they contribute to your life. And mind you that those of you who take these things seriously should be working while you are students. It is not when you graduate and go on youth corps. You will have skills and you have things to do that you can do for other people. So those who listen to me now and take it to heart, they will be making money while they are undergraduates. And those who don't listen might still be eating their papa's food long after they have forgotten about university. I don't want you to be in that kind of place. So basic skills and projects. You are expected to keep increasing your 3D modeling skills concurrently with the materials given in these lectures. The videos offered by software manufacturers are not alternatives to my videos. I expect you to watch all relevant videos and improve your skills. My videos are to prepare you for applying the knowledge to projects. We do not learn in a vacuum. We learn by using the knowledge to do specific useful products. Therefore, in teaching you parametric design, I'm not just going to be telling you about the theories of parametric design. We are just going to be walking through one example after the other, after the other, after the other. And then your project and homework would be for you to also use the same knowledge to do something useful. Parametric component design. We will gain valuable skills and experience in the use of both the graphical user interface as well as the applications programmer interface to learn how to create parametric 3D models. Among several uses of such models are scenario analysis for simulation and optimization. That is a key step in design. When you design something, you want to analyze it. For instance, you design a connecting rod. You want to put loads on that connecting rod that are similar to the loads that connecting rod will get in real life. And you want to see that that connecting rod survives the application of those loads. If it doesn't, you want to know why it doesn't. You want to know where it doesn't. You want to know whether you need to add more material, make it thicker, make it longer, make it fatter, use better materials. The results that you will use to take those decisions come from your scenario analysis, from simulation and optimization. And Fusion 360 has the facility for simulation and optimization. When you finish that, you also go into manufacturing. The easiest way to manufacture right now would be to just send it to a 3D printer, but it doesn't have to be like that. We are beginning to see CNC machines, and we are beginning to see 3D printers that can print metals. So as the technology is going on, that means that most of the work of making products are going to stay at the design end. And just like you have software as a service, you are going to have products as a service. People, the turnaround time to making new products is going to increase, and it is the people who are doing what you are doing now that will be left. The traditional machine workmen and all those ones, they are going to be a thing of, they are going to go with this, like the dinosaurs eventually. So I'm not laughing at them, but I'm just saying that people need to retool, and it's an opportunity and an advantage for us who are in the have-nots of the world. Because when these things begin to work, those of us who train to be this way will be able to get good jobs and will be able to do things that were probably not thought possible for us. So that is going to come from parametric component design, which we will talk about as we talked before. The project basis, I told you that the project basis are internal combustion engines and turbines. Last week, we will see situations where the GUI may not even be available to use, because you may have difficult problems that you need to program to do, or you need to use third-party programs. Those examples may come up when we are looking at turbines and centrifugal pumps. We shall be focused on two main projects for the rest of the term: creation of the engine of an internal combustion engine and water turbine. I know it is more logical and appropriate to be focused on electric vehicles, but there are two reasons we will begin with the internal combustion engine as our project example. And we explained that last week. The graphics and design issues involved are more interesting, they are deep, and they will help you hone your skills in graphic design. So even if you are not going to make any internal combustion engine, learn how to work and how to make those components. You will be learning a lot. And then you can use that knowledge in making electric vehicles, which will be simpler to do than this other one. Second, the jury is still out on the eventual winners of the successors to the internal combustion engine as the primary means of transportation. Internal combustion engine has reigned supreme for 150 years. And everything, whether it is rail, even ships use internal combustion engine. When you see a ship whose name starts with MV, it means motor vehicle. So essentially, it's using the same kind of idea as your car. May not be using petrol, but it is still the same internally combusted fuel that are really driving it. Even some aeroplanes, some other things that are moving you in one way or the other. So these things have really reigned supreme for a long time. So, but we don't know what the successor will be, whether it will be electric. Many people think it's electric, but some people are betting that it will be hybrid or hydrogen reactors that would actually still reign. We don't know. So just hold your skills and you don't know where your job will come from. Now, the second set of projects will be turbines and pumps. I'm bringing those into this lecture. Energy is a major issue for us in Nigeria. We will use this to demonstrate and gain skills in the API that we can use to solve Nigeria's energy problem. Internal combustion engine components. There are three main moving parts in the internal combustion engine: the piston that compresses the air-fuel mixtures and takes expansion pressures during the combustion to drive the crankshaft through the connecting rod; the crankshaft that drives the wheels through the gears and the drivetrain; the connecting rod that transmits the reciprocating motion of the piston to the rotational motion of the crankshaft. Actually, I have a complete drawing from the beginning of your basic sketch of connecting rod or the revolution or the revolve of your piston to the modular design of your crankshaft. I have everything done, but I'm not giving you until the end. I want you to have your own ideas. I will show you what I am doing, but I want to be able to press you to think maybe you'll get better solutions. Maybe you'll do some things better than I have done. So I don't want to constrain you with my own example, because if I give you my file, you will just copy it and you will not think. And that's not going to be good for us. So the connecting rod is an example of motion transmission I told you about 2 weeks ago. I said you should look for motion transmission, where the thing transmitting the motion passes the motion through another object to a third object. We started looking at that when we looked at the drawer cabinet, where the slider was transmitting motion and displacement between the body of the equipment itself and then the cabinets that can move, the drawers that can move back and forth. And what is in between them? The middle man there is the slider. But that same kind of work is being done by the connecting rod. In the case of the connecting rod, it has a reciprocating motion at one end, and it has a rotatory motion at the other end. On the crankshaft end, it's rotation. On the end, it's reciprocating motion. So that is a very good example of motion and displacement transmission that might be of interest to you later on, whatever engineering you do. The engineering in this thing is that it cuts across. Mechanical design is very important to all engineering, because even if you are doing electrical engineering, electricity, the thing is going to be resting on something that is physical. So mechanical design will still be relevant even for that. So this is an example of a connecting rod that I did this one from scratch. So I have the file for this, and I'm just using it as an example where we do one together in the class. The connecting rod motion from the piston to the crankshaft, the former is reciprocatory, while the latter is rotational. Another example of the connecting rod was discussed in the Autodesk video you were to watch 2 weeks ago. It's the same idea. And I hope you have gone back to that video, because their videos are fast and they don't type. Well, I don't know whether you hear them or understand them better than you understand them, but whichever one you understand better, use. Some people may understand them better than me. I don't mind. Some people may understand me better than them. That's okay. You can have both. It's not an either or. The connecting rod. This is an example of, here's an example of the connecting rod, not of the piston. Sorry, that's a mistake there. Let me just correct that straight away, because it has made it to another node. Okay. So here is an example of the connecting rod. To see the full steps to create this and subsequent models, which watch the 1 hour clip on Vimeo by O.A. Fakilede, Moving Parts. I think I supply you the full citation to be able to reach that if you want. This was done 7 years ago, and I used an older version of Vision 360. So that's why in teaching you, I'm not just giving you that. I want to repeat it so that the version of Vision 360 you are using, you can follow the steps without asking why something is not there. We'll begin this project by sketching and extruding to make a piston like this one. Note that there is a big pin. This area is what we call the big pin. That's the one that holds the crankshaft. And this small pin is connected to the piston. Note that there is a big pin that holds the crankshaft and a small pin for the piston. Those are the two. Now, even at the connected at the crankshaft, we still break that pin into two, so that it's only in an assembly when we join them together, holding them with pins, that it will become round. That is how it is, and this is there for the purpose of maintenance. If it was one designed like this, then you make the vehicle only once, and when there's any problem, you throw the vehicle away, which would not be economical. The connecting rod assembly has two main components, the head and the body, as shown here. This design has the practical purpose of easy disassembly for maintenance or replacement. There are pins that hold this in place, and there is a remover of material to create a hollow part in the main body of the connecting rod. See, what I mean is this one. There is not this particular hole there, which you will still see later. I will show you. It serves no purpose other than saving money and saving weight. Because when you do scenario analysis, you will see that even if there was material here, it will be carrying close to zero load. So any material you put there is wasted. So why don't you remove that material and reduce the amount of material that will go into your piston? That is the reason why that hole is there. So when you see somebody design a piston that doesn't have that space, it is not impossible that the piston is not optimal, that is using more material than it needs to. Okay, so there are pins that hold these two in place. There is a remover of my, okay, now how large should this hole be? How large should this be is a matter of simulation and analysis. That's where this decision to remove that will come from. But before you go to simulation analysis, you have to first of all have a correct drawing. It is that drawing in several scenarios that will now show you which one is actually giving you the best result. And the piston, this is how the piston, this is the piston that I designed in that drawing. So I show you the steps. You can find the steps in that video of how to make exactly this one. We already know what the piston does. And then the holes you have there are the pins that will hold that small end. This small end of the connecting rod, this small end of the connecting rod is what will be held by the pin inside this that will now hold this into it. You will see how all of them work together as we move on. Okay, that is it. You can see that the small pin is inside the piston here, and then the big pin is connected with the assembly here to the proper place in the pin of the crankshaft. And this is a single engine where there are no other engines, so you don't have to think about the firing order and so many other things. I think I told you to read about firing order last time. So I would see whether some of you have something to tell me on the chat room about that today. And then, for instance, the engine that I will do for you, you will tell me what the firing order is. And that will let me know whether you actually went to do the homework I gave you. Here's an example of the crankshaft. Here's the example of the crankshaft and the single engine cylinder in a snapshot of its motion. You will see an animation of the motion in some of the videos I'll share. While the piston reciprocates, there's an oscillatory motion around the small pin inside the piston. So what we are saying is that as this thing is going up and down, there is some reciprocating motion, this left and right, left and right, left and right here, that is going on here. It's a very complicated motion, but you'll be surprised. To create the motion is a matter of creating the correct joints and allowing the motions to be subject to the constraints that those joints give, and everything will be done correctly. So you don't need to worry about the complication of the motions. While the V engines and multi-cylinder inline engines can be designed from this single engine and the drawing in the given reference, as the drawing in the given reference clearly shows. So with this single engine, this single cylinder, we can now decide to make it a V engine or make it an inline engine, and you'll see how that is done by some of the drawings that will come in this multi-component parametric design something. For instance, for you looking at this now, it may not be obvious that this single cylinder, as this single piece of the crankshaft, is exactly what we replicated several times to make this crankshaft. For all you care, just notice that at every period of this thing, it's exactly the same, but with some rotation. That's all. And the rotations are the things that enforce the time, that enforce the firing order. If they were not rotated with respect to one another, the engine will not work. It is this rotation to affect a particular firing order that make the engine run smoothly. And by the time you understand this, you are already understanding some of the issues in this thing, even though you are not necessarily being trained to be an automotive engineer. And who says you will not be in the automotive industry? We don't know. So when you are in the university, even if you study something else, you will be surprised. I remember when I graduated from Lagos University many years back, 3 of my friends went to work in Shell. One did computer science, another one, I think, did physics, and another one did mechanical engineering. Eventually, in Shell, they all did the same thing. But you'll be surprised who was the boss at the end of the day. The boss that eventually rode to become the managing director of the whole organization was a guy that read computer science. So you never can predict where you are. International companies, they go with your background and they are going to make you what they need in their company. You cannot predict that beforehand. So don't just assume that you already know what you will do. There's nothing stopping you from ending up the automotive industry. So you remember last week, we did the connecting rod by just sketching seven circles. See the 7 circles? And then we did that on the YZ plane. I like to start everything on the YZ plane. And then you remember when we did it, we just did these concentric circles. We put this one somewhere vertical, and then we use the horizontal vertical constraint to force them to be aligned vertically. And then we applied dimensions, and you see that most of what we have here are in black, which shows that they are not movable. They are fixed and they have been properly fully specified, except this one that was still in blue, which can easily be remedied anytime we want. There is a 10-minute video on the sketch. I think I will avoid that now because we've taken a look, or maybe let me see the class wants. You already have what I gave to you before. Should I take you again through the video or just move on to new material for today? Class, I want your participation here. Opinion? Should I take you? Okay. So most of you are happy with what we already did. So move on. Okay, good. So you already have them, so there's no need to spend unnecessary time on that. Good. Okay, so when you watch that video, what you will see is that instead of designing a connecting rod like this is what that video ends up designing. So then I ask, do these two look alike? And if they don't look alike, what do you do? How do you make this one that video helped you to design? How do you like this one? And then from there, we add another video clip, the connecting rod 1, which helps us to see how we decided to go on the XY plane and did another sketch and did 2 extrusions. One extrusion to create a join and the another extrusion to create a cut. And by the time we finished those 2 extrusions, we came up with something. By the time we finished the first extrusion, we came up with something like this. And we noticed that there was still material that was blocking the pinholes that we created. And some people in class suggested that the way to solve that problem is to do a cut extrusion from here, and cut it through. And that's what we did. And as we did it, as this is the dialogue that we used to achieve that. With this dialogue, we were able to cut through, and everything now, we are now able to see this kind of picture. And then we created 2 components by cutting at the coordinate XY plane and just moving an extrusion, a cut extrusion through a very small distance, like 0.1 millimeter or something even smaller. And it cut the plane into 2. And once it cut it into 2, we now get this, which is now very similar to this one. Now, these 2 are very similar, but I want to see how observant you are. Do they look alike now? Well, of course they do. Can you tell me what the differences still are? There are differences. Even though I was the person that did this 7 years ago, and I did this last week, can you tell me if you can notice some differences between these 2? I want you to know there are differences. Can anybody detect those differences? I'm waiting for you in the chat room to see. Let me put the question there. there are less shapes from the sketch. I don't understand your English. Elion Aki Onitolo. Please, can you say it in Yoruba? Because me too, I can speak Yoruba. This your English looks too advanced for me. I don't understand, seriously. The opening of the sides for the new ones are cut longer. Okay, you are talking of the separation between the two. No, let me tell you. If you look carefully, you will see that this new one is not as wide as the old one. It's not as wide as the old one. Yeah, this one is narrower than this. That is the fundamental difference. Most things are equal, but this is whereas in this place, the hole that we put here for the pin did not cut into the larger cylinder here, but this hole cut a little bit to this cylinder. So you can notice that if you just take a cut through it. If I can quickly get to the Fusion 360 file, I can do it for you to see and compare the slicing through both of them. You'll see that this is narrower, and therefore this cylinder here, this cylindrical object here with this small thickness, there is something that cuts it through, cuts part of it here, and here it is completely free of the cut of this hole. That was why when we were extruding a cut, it was the cylinder we were cutting through. When I did this, that problem did not arise because I put it a little bit further away. But that means that I had a connect. Okay, let me not release the answer to the question I want to ask. Which of these two do you think is really a better connecting rod, all things being equal? Don't forget that both of them have the small pin and the big pin. Both of them have that carved out area where you reduce material, but this one is slightly bigger than this. Which one do you think is better of these two from a designer's point of view? Which of these two? You can call this one left and call this one right. The left, the newer one. The testimony says the right. You are the only one that is different. Let's see whether anybody will support you. Anybody supporting testimony? Okay, testimony. Okay, Onyi Consola. You are still in the minority. Can you explain to me? Can you explain in a type something in the chat room why you think the right, Onyi Consola or testimony, either of you? Can you tell why the right one is better? Before I ask one of the people, and the people who think the left is better also can go on. I will be reading. I'm reading your chats. Tell me which one you think is better and why. And what basis? What's the objective function that makes one better than the other? All else being equal, except the fact that this one is the right one is wider than the left one. Any reason? I'm still waiting. I'm in the chat room waiting, looking at you. I think it depends on the size of the crankshaft. No, it doesn't depend on the size of the crankshaft. Both of them will fit. Whatever crankshaft this one fits, this one will fit it exactly. Both of them, because what will determine that is the internal radius of the big pin. I think it is better because the motion is faster. Why would the motion be faster? I can't see. You have not even seen any motion. Why do you think it will be faster? Don't see it. I can't see that. Okay, let me ask you, which one will have a higher moment of inertia out of these two? The left or the right one? Which one will have a higher moment of inertia? Left or right? Which one will have a bigger moment of inertia? The right will have a bigger moment of inertia. Okay, Ebenezer Shudipo, you are wrong, because there is more weight further away, because it is the weight, is an integration of weight multiplied by the square of distance from the point of for the point you are rotating about. So the right one definitely has the bigger moment of inertia. So does that make the right better or the left better? Knowing now that the right one has a bigger moment of inertia. Okay, maybe it makes the left better because there's less energy used to be moving it. And because as much as possible, you want your force transmitters to be as transparent as possible and not take the energy for themselves. So that's the thing. So it will take more energy to run the one on the right than to run the one on the left. And that energy is not energy that is driving your vehicle. The advantage, if any, of this one is that it will have a higher inertia, and then maybe saves, maybe you will have a longer braking time and your engine will run idle. When you turn it off, it will be longer distance. Anyway, that is just, but I didn't design it for that purpose. It just happened like that. Okay, so let us move on. Okay, so read about four-stroke engine and firing orders for next week. Now, can anybody tell me what they know about firing orders? Did anybody actually check anything about firing orders? I want to see if there's anybody in the class that did anything on firing orders. So let's see. Firing orders. Anybody? Can anybody tell me anything they know about firing order? And it would be interesting if somebody even can tell me what the firing order of the 6-cylinder inline engine that I gave you in the clip. Did anybody in this class find out anything about firing order? Okay, I have me see God's favor. What is 153624? Okay, good. Show the one. But I have me see. Are you sure that that is the firing order in okay, the sequence? Good. Olajide, sequence of power delivery. Good. Correct. But I'm interested in the guy who thinks he knows the firing order of the engine that I gave you. 153624. How did you, I have missing God's favor. How did you find that? All the pieces can move at the same direction. The firing order is sequence of motion. Yes, but I'm still waiting for, I still want to hear from Ahamisi God's favor. Did you just guess or you know? Ahamisi, I'm waiting for you. Guess or no? Ahamisi, you are dead wrong then. Yes, I wrote it down somewhere because I calculated it, but I wasn't using things that were there in the normal, because the fact that something is common doesn't mean that that's what I gave you. No, I didn't just give you something that was common. Okay, let us move on. I will talk about that. I will give you what that is. We will do then we did a simpler connecting rod. This time, the connecting rod we did when we were doing the parameterization is simpler than what we did before. Who can remember what is the fundamental difference between the connecting rod of the parameterized design compared to the connecting rod of the GUI design? What was the main difference? What was the main difference in that connecting rod? Let me type the question. Let me see this. What's the main difference between the connecting rods of the parameterized con rod and the GUI con rod? What was the main difference? You remember we set some parameters and then we had a video clip of 40 minutes that showed you how it was done. I don't have any picture here. So maybe I should just this is the last thing we did. Let me just give the clip before we go for break. And then when you come back for break, we will just have new materials to look at. That's parameterized control. Let us just take a look at it.